Hello everyone, welcome to my channel IB Crocodile, which is specialized to provide supporting videos for both IB physics and mathematics analysis and approaches, AA programs both on the SL and high level curriculums. So today I'm going to discuss the derived physical quantities in mechanics. In previous videos, I discussed the fundamental quantities, the seven fundamental physical quantities. And if you need more, let me share it with you first. Okay, so if you need more details, the screen here, shows the seven fundamental quantities. And we have like a full video in more details about all of them, and even more supplementary quantities. And you can check the link and look for more videos in the channel. Okay, so these are the seven fundamental physical quantities: length, mass, time, the temperature, amount of substance, electric current intensity. I like to call it, this is really the right way. It's not current. Current is just flow of electrons, but the physical property itself is called electric current intensity, I, in ampere. And then the seventh one is luminous intensity, and as I mentioned before, it doesn't have any role in this program in IB, either on the SL or the high level. So it is just there for completeness. Okay, so what is the idea? So any other physical quantities will be called derived rather than the seven fundamentals. Okay, so by definition, derived physical quantities all other quantities are related to and have associated units, so they can be expressed in one or more fundamental unit. And this is actually a very important skill you need to develop, during the program, to be able to express any derived quantity in its SI fundamental units. Okay, but of course there are so many derived quantities in physics and so many branches. So today I'm going to focus only on derived quantities in mechanics, topic 2. Okay, so the first quantity I would like to mention today is, let's say, area. So we say, okay, so we say length is fundamental, but area is not fundamental. Okay, so let's say, okay, so area is basically what is length times length, right? We say area of a square, for example, length or side by side, or area of a rectangle, length by width. So it is basically length times length, right? So this is basically area. So since length in meter in SI system, so area is going to be in meter times meter, which is meter squared. Okay, so meter squared is a derived unit, right? Can be expressed in one fundamental unit. The second derived quantity, let's say volume. So volume, let's say volume of a cuboid, length times width times height, right? Or volume of a cube, let's say length by length by length, or side like edge length by, to the power of 3. So basically, again, so volume, fundamentally is just length times length times length. So volume can be, the unit of volume here in SI system, okay, is meter times meter times meter, which is meter cube. Okay. For example, let's have an example here of another unit. For example, let's say I have a volume of a cylinder, for example, like 1 millimeter cube. Okay, so 1 millimeter cube need to be converted into meter cube. So I know 1 meter is 1000 millimeter, or basically milli as a prefix is 10 to the power of -3, right? But since, this is a common mistake, to many students, I hear like, I heard them saying, okay, so this is 1 times 10 to the power of -3 meter cube, which is not right. because we have millimeter times millimeter times millimeter. So you need to actually convert each dimension by multiplying, by 10 to the power of -3. So here is going to be 10 to the power of -3, all to the power of 3. And that will be in meter cube. Okay? So, which is 10 to the power of -9 meter cube. Okay? So that is area, volume. So let's now the next one, just, kind of logical order here. So density. So density is the mass per unit volume of a homogeneous matter. So density is mass per unit volume. So always, I like to look at the formula, and then from the formula, I can derive the unit, right? So mass itself is fundamental, but volume is not fundamental. Density is not fundamental. Both of them are derived. So what is the unit of mass? Is kilogram, right? Unit of volume, we just discussed, meter cube. So basically, unit of density is kilogram meter -3. And in IB, just a hint, we don't actually use slash as a convention. We use always like multiplied by the unit to the power of like a negative form. Okay, so as a convention, we don't use per meter cube. We use kilogram times meter -3. You will actually notice this during the program. Okay, so now I was able to express density in its fundamental units. Kilogram is fundamental, meter is fundamental. So density is derived. So now this is the scale that I was talking about. Expressing any physical quantity into its SI units. Okay, so area, volume, density. Next, we'll talk about speed. Okay, so speed, by definition, is distance over time. Very simple, So for example, here, if an object or a cyclist or any moving object, covering the same equal distance over the same intervals of time. So that means it's a uniform motion. It is a constant speed. And if the speed is constant, I can use distance over time. If the speed is not constant, I cannot touch this formula. But for the sake of the purpose of this video today, I'm going just to present the derived quantities. I'm not going to talk physics, like the different, between like more mechanics and motion. Maybe later videos, I can elaborate more on difference between speed and velocity and acceleration and what kind of equation we need to use. But today we just need to get the expression of derived quantities. So speed, distance over time. So distance in meter, time in SI system, second, not minutes, right? So that means that the speed is going to be meter second -1. Now, if the speed is not constant, or let's say velocity is not constant, so that means there is acceleration. So acceleration by definition is the rate of change of velocity. Acceleration by definition, again, is the rate of change of velocity. And when I say rate, it means over time. So acceleration, okay, sample acceleration is A, is equal basically to delta V over delta T. Okay. Now, the speed, or the magnitude of the velocity is the speed, meter per second, right? And then time here we have second. Okay, that leading that the unit of acceleration is meters per second squared, or meter second -2. Okay, so that is the expression of acceleration in SI unit. Okay, now if you know speed, if you know acceleration, what can you know now? Force. Newton's second law. So force is equal to mass times the net force, basically. The net force is equal to mass times acceleration, right? Now, since now we know that, okay, the mass is fundamental, in kilograms. Acceleration is not fundamental, but we could express acceleration in its SI system as meter per second or meter second minus 2. So that means force is in kilogram times meter second minus 2. Make sense? And then we call this unit Newton. So we call this unit Newton. So I can say 1 Newton. It could be an easy paper 1 question, multiple choice. What is Newton? What is 1 Newton? 1 Newton is 1 kilogram times meters second minus 2. It all back to the basics. Come back to the basics, the skill to derive, to express the physical quantity using the formula. I'm just using the formula and then derive the quantity or the unit basically. Okay. Now, if you multiply force by displacement and giving that the displacement is in the same direction of the force, so we'll end up with force times displacement is going to give us work done. So work done is force times displacement. Now, force now is in Newton. Okay. Force in Newton and displacement in meters. Okay. So that means work is Newton times meter. Then, but we actually now have Newton in SI system. Newton is mass times acceleration. So we can say, okay, so that means also Newton is, I can like break down Newton or express Newton as kilogram meter second minus 2, and then we have one more meter there. So the final answer here is going to be kilograms or kilogram meter squared second minus 2. Of course, you don't have to memorize this. You need to know how to find. Okay. So kilogram meter squared second minus 2 from the formula. Work equal force times distance. But then also we give it a name. So this unit here, we call it joule. Joule or J, right? So now we can now say 1 joule is 1 Newton times meter, or 1 joule is 1 kilogram meter squared second minus 2. There is another formal or informal definition of work. Work done is, it can be also like the energy transferred or equivalent to the energy transferred from one point to another. And that energy, for example, it could be kinetic energy, potential energy, gravitational potential energy, and so forth. So we end up actually unit of energy is also joule. So work energy, they have the same unit, right? Because they are very related, right? Work can be expressed as energy change. For example, let me give you just a quick example just to understand what I'm saying, what I'm talking about. We have an object initially at rest. When I say at rest, what does it mean? At rest means the velocity, or let's say initial velocity, is 0 meter per second. Now, this whatever, let's say we give a push to this object, and then this object could move with a certain velocity, right? And reaching, let's say, final velocity at this point here, let's say at this point of time, I don't know, 5 meters per second. Okay. And then this force here, let's say, I don't know, 2 newtons. And we've got a distance traveled from the initial position to this position now here is 10 meters. Okay. Of course, these numbers may not match. I just want to make a point here. So what I want to say, okay, or let's say we don't know the distance or the displacement. Let's say d. Okay, so we have the distance here, d. Okay, so now let's say, okay, so now the force or the work done here is going to be the force times the distance, right? Which is 2 Newton times d. But at the same time, the kinetic energy at the initial position here is 0 because the velocity is 0, right? And the kinetic energy at the second point or the final position is half mv squared, right? So we say kinetic energy at point 2 is half mv squared, right? So now we say, okay, so now we say now this object gained a kinetic energy due to the change in velocity from 0 reaching a final velocity of 5 meters per second. And now that change in kinetic energy is basically the work done should equal exactly the force times the distance. So if I know the mass of this object, I can back calculate the distance. Okay, so the bottom line here, energy and work are interrelated. Work can be or is equivalent to the energy transfer from one point to another. So once you know now the unit of work is joule, so unit of any kind of energy is joule, right? Thermal energy in joule, elastic potential energy in joule, and so on. Very good. So now we got force, we got work and energy. Now if you divide or the rate of doing work, and say the rate means over time, so work over time, which will give us power. So here P here is power. You will see lots of P's in the program, but just need to make sure which formula you talk about. So power is work over time. So work now is in joule and time in second. So that gives us the power unit is joule second minus 1, right? But then from the previous example here, we know joule can be expressed as Newton meter or kilogram meter squared second minus 2. And then I have second minus 1 because of the time down here at the denominator. So joule second minus 1 can be like at the final answer is expressed in the fundamental SI unit kilogram meter squared second minus 3. And we call this unit watt. So 1 watt is 1 joules per second, is the rate of doing work. It's power. And this is the SI unit of watt, kilogram meter squared second minus 3. Again, I never memorized this. You don't memorize this, but you can find it in 5 seconds. Okay? So that is about the power. Okay, now the next one is momentum. Momentum by also they call it P. They give it a symbol of P as well, so be careful. They have lots of P's in the program, as I said, so you just need to know what is this. So this is a momentum. Momentum is the product of mass and velocity of an object that is in motion. Okay, so an object that is in motion will create a momentum, and the momentum is basically the product of its mass and the speed or the velocity. Okay, now mass is SI system, kilogram, fundamental, speed, velocity, meters per second. So now that means momentum in kilogram meter second minus 1. Simple as that. So this is the unit of momentum. Okay, so let me just write it down here just to make sure this is not power. This is momentum. And then, of course, delta P. Delta in physics means change. So say delta P, if P is momentum, so delta P is what? Is a change in momentum. Okay, well, change in momentum, do you expect different unit of change in momentum? No, that's what I thought. So it will be also kilograms meters second minus 1. But then we call the change in momentum, we call it impulse. So this is another different physical property than momentum. Momentum is just momentum at certain condition. But change in momentum from two velocities, let's say from velocity 1 to velocity 2, right? So this is delta P, and we call it impulse. So impulse is the same unit as momentum, kilogram meter per second, but as physics, there are two different quantities. And actually, we can link impulse to the force, right? So when we say, okay, when we say the net force according to Newton second law is equal to mass times acceleration, right? And then I say, okay, acceleration is delta V over delta T, right? So I can say, okay, m times delta V actually is change in momentum. So I can say that numerator becomes delta P over delta T. And basically delta P, we call it impulse, pi, right? And this is the net force or average force sometimes. So I is going to be the force times delta T, which is Newton second. So kilogram meter second minus 1 should equivalent or be identical to Newton second. Newton time second. And this is easy to prove. So we know Newton is what is mass times acceleration, which is kilogram meter second minus 2. And then you multiply by second here. So you end up with kilogram meter, okay, minus, sorry, this is IF Newton times second. Yeah, so mass kilogram meter second minus 2. This is Newton, and then times second. So you end up, yeah, you end up with kilogram meter second minus 1. Yeah, which is basically the change in momentum or the momentum here. Okay. So this is basically most of the derived quantities in mechanics that you're gonna see. I hope that is helpful. Please feel free to leave any comments or questions. And for more details or information about my channel, you can always check the links. And good luck, and see you in further videos. See you.